Hello, everyone. Today I'm gonna start a new chapter, new topic, which is called Thevenin and Norton Equivalents for resistive circuits. So given that you have a circuit, suppose you have a circuit that is resistive, meaning that you only have some bunch of resistors and some sources. It could be independent sources, or it could be dependent sources. So these are the only elements that you have, just resistors and sources. Current source or voltage source, again, could be dependent or independent, doesn't matter. So somehow you want to now find an equivalent circuit for that. And let's say from point A and B, so you want to find the equivalent of this circuit. So you have seen R equivalents before. Remember, you only had resistors and dependent sources. You could find it at R equivalent. So this Thevenin and Norton equivalents are basically somehow the extension of them, where in this case, you also have independent sources. Okay, so when you have independent sources, at the end, your equivalent will also have some sources. See, because if you didn't have independent sources, you only had resistors and dependent sources, then there was no source of energy. So if you didn't have any source of energy, your equivalent would be just a resistor, okay? However, in this case, because you have sources of energy, at the end, your equivalent will also have a source of energy. So now we see two equivalents. One is called Thevenin equivalent, where you can model your resistive circuit with a resistor in series with a voltage source with the value of Thevenin. Okay, so from point of view of A and B can be, the circuit can be modeled as the R Thevenin in series with a voltage source, or you can model this with a current source and the resistor. Remember the source transformation. So basically any voltage with the resistor, voltage source with the resistors in series can be modeled with the current source in parallel, right? So the source transformation idea. So the same here. So you can again model the whole resistive circuit with a current source and in parallel with a resistor. The resistor called R Thevenin, and it's the same for both of them, the same resistor, similar to source transformation. If you remember, we had the same resistor. However, here we have a voltage source with a value of Thevenin, and here we have a current source with a value of I Norton. Okay, so they are named Thevenin and Norton equivalents. Okay. And based on the source transformation, you already know that there is a relationship between V, I, and R, and is that V equal to Ri. So V Thevenin equal to R Thevenin times I Norton. Okay, so there's also a relationship between these parameters. So now in this chapter, we're gonna study how we can find this R Thevenin, how we can find V Thevenin, and how we can find I Norton. Okay, so let's start with that. Okay, so again, suppose this blue box is your resistive network, and you would like to model it with a source, voltage source, and a resistor, okay, like that. So from perspective of, again, node A and B, these two should be the same, okay? So now, therefore, let's look at this circuit. So if I have this circuit, and if I look at if I open, like A and B, let's say it's open, so what voltage do I see here? We call it V of open circuit. So if there's nothing connected to A and B, it's just open. So what do you think the voltage of this voltage would be? VAB, okay? Because it's open, the value of I is gonna be 0, right? Because it's open, the current is 0. When the current is 0, the voltage across this R Thevenin would be also 0, V equal to Ri, right? So the voltage across this is 0. So I hope everybody agrees. Then V open circuit will be exactly equal to V Thevenin, or you can look at it as like a KVL. If you write the KVL, let's say started from here, negative V Thevenin plus here 0, because there's no current. So the voltage is 0 plus V of open circuit equal to 0. In other words, V of open circuit is equal to V7. Okay. So what this says that, so if I open this and I see Thevenin, so there should be the same thing on the big circuit that I have. So if I open my circuit at the node point A and B, and if I measure the voltage, V open circuit, this V open circuit has to be equal to the same as this circuit. So V open circuit has to be equal to Thevenin. Okay, so this is ideal then. Therefore, so if you want to calculate, if you give me a circuit, and if I want to calculate Thevenin, I have to just look at the V open circuit. Okay. So that's something that you need to remember. And this is the idea behind that, because in the equivalent, when it's open, the open is exactly equal to Thevenin. So they should be the same also with the original circuit. Okay. So let me read from here. The open circuit voltage at terminals A and B in the circuit shown, and B is equal to Thevenin. So therefore, this must be the same for also our resistive circuit original. So I just open it and I measure the voltage open source, and that's equal to Thevenin. Okay, so this is how we can find, and we are going to see, of course, many examples. So that's how we can find Thevenin. We just open a circuit, look at the V of open circuit. So now next question is that how we can find R Thevenin. So R Thevenin is almost all the steps are similar to R equivalent, remember, but there's only one difference, that when we, like in previous cases, when we look at R equivalent, remember there was no independent source here, okay? That's why the whole thing, we could just measure it with what on R equivalent. But in this case, we also have independent sources. So somehow we have to calculate R equivalent, we have to, or R Thevenin, we have to get rid of them. So what we do, we zero the independent sources, okay? So that's the step that you have to take. To calculate the R equivalent or R Thevenin, you zero all the independent sources. Again, the idea is that I just want to know the resistance of the circuit. So I have to get rid of the sources of energy. So I zero the sources of energy. If it's a voltage source, I short it. If it's a current source, I open it. Okay, so you zero all the independent sources. And then you're left with a circuit, which has, of course, a bunch of probably resistors and some dependent sources. And dependent sources are totally fine, because we have already seen dependent sources do not generate any energy by themselves, right? So they can act like a passive network. So they are like, you can find R equivalent for that kind of circuits, right? Okay, so therefore, you just do, however we calculated R equivalent. Remember, one of the techniques was to apply a test voltage, V of S, and then find IS, and then look at the R equivalent equal to VS over IS. So this step, after you zeroing all the independent sources, the next step is similar as before, or the same as, similar to finding R equivalent as you had seen before. Okay, but again, the only difference is that here you will have some independent sources. And if you do have independent sources, you have to zero them to calculate the resistance of the circuit. So there are two different things. A circuit will have a Thevenin, which is source of and generating energy. And then there's a resistance. Okay, to calculate the resistance, you have to basically zero the sources, the independent sources. Okay, so to recap the Thevenin equivalent method, you open circuit, you measure the voltage or calculate the voltage, that's Thevenin. And then you have to find the R Thevenin or R equivalent. And if you have a dependent source, usually we put remember as before, we put a test voltage, Vs, and then calculate Is. And then Vs over Is gives us the R Thevenin. Okay, so with that, let's look at examples. Okay, so this circuit is given, and we would like to find the Thevenin equivalent from point of view of A and B, so between A and B. Okay, so eventually after we calculate, we have to find R Thevenin, and then we have to find V Thevenin. This is what we have to do. Okay, so to calculate V Thevenin, remember that's open circuit, so you have to open it. Here is just open. In some situation, it might not be open, it might be connected to something, but we have to do it ourselves. Okay, we just open it. Okay, and then we look at the voltage here, voltage VAB across here, which we call it also V of open circuit. So this is basically V of open circuit, which is equivalent to V threshold. Okay, so let's calculate that. At this point, any technique, because we have to analyze the circuit, any technique that you know, node voltage analysis or mesh current analysis, or might be other techniques that you might use, you can use. It's, as you know, there's not a unique solution usually. So to just calculate the V of open circuit. Okay, so let's do that. Now, because it's open, this is a good thing that when we open it, again, the current is 0. So this is the first thing that I will write. And then I want to calculate this voltage. Let's do node analysis. Again, this option up to you what analysis that you want to do. But in this case, node seems to be a good option. So this is one essential node. Call it V1. This is another essential node, reference node. The voltage is 0. Okay. And let's write the KCM and this V1. Okay. So starting from here, this is V1 minus 25. So V1 minus 25 divided by 5, it's this term. And then plus V1 minus 0 divided by 20, this term. And then it's a big node, right? So remember, you have to also look at this current, this current, this current. There are 4 branches. We wrote this, we wrote that, and then this current is -3, right? So it's -3 going down. And how about this current? This current is 0 because of open circuit. So now you use the fact that it's open. Because this is open, this current is equal to 0. So as you see, there is no term there. So that's the whole equation, equal to 0. So there's only one unknown, V1, in this equation. We just solve for V1, and V1 is 32 volts. Okay, so that's V1. That's V1. But that, I would say that V1 is equal to also VAB, or here, V open circuit. The reason is that because, again, this is I equal to 0, so there's no potential difference across this 4O. So from here to here, there's no potential difference, okay? This is 0 volts. So whatever you have here, it's gonna be also on this, and this side is also 0. So this is 0, this was 32, so this V1 is 32 volt, right? So this is 32 volt, so this is also 32 volts. Because there's no potential difference across 4 ohms. Okay, perfect. So VAB, or V open circuit, happens to be equal to V1, which is 32 volts, and that's also V Thevenin. Okay, perfect. So again, this is the explanation here, because the I was 0, potential difference across 4 ohm is 0, so you get everything that is here, 32 volt here. Okay, good. So this is our V Thevenin. Now we have to find R Thevenin. So for R Thevenin, again, for this circuit, remember, you have to get rid of all independent sources, because I'm only looking to find the resistance of the circuit, okay? So I shouldn't have any basically independent source, because I just look for the resistance of the circuit. So you get rid of these guys. Zeroing a voltage source means I have to short circuit it. Zeroing a current source means that I have to open it. Okay, so let's do that. So that's the first step. Zero all the independent sources. So I short circuited here and I opened this one here. See, shorted this and I opened this. And then copied everything else. And this is not A and B. I have to look at the R equivalent. So after you zeroing the independent sources, everything else is like as before, R equivalent. Okay, so what's R equivalent here? That's a simple case because we don't have any dependent sources, which is good. Us only resistors. That's good. We don't have any dependent. Remember, when we have a dependent source, then you have to do Vs over Is. But in this case, it's just only resistors. So look at here. This 5 and 20. They're connected from this side and they're connected from that side. So those two are parallel. Hopefully everybody sees. This 5 ohm is in parallel with 20 ohm. And then after you calculate this, which is 520 divided by 5 plus 20, then apparently it's going to be 4 ohm. Then that 4 ohm, which is here, the equivalent of this, is in series with this 4 ohm. Okay. Okay, so this 4 ohm is in series with the other 4 ohm. So you add them, you get 8 ohm. Okay, so our equivalent is 8 ohm. And this is the Thevenin equivalent of this circuit. So we have Thevenin, which we had calculated above 32 volt, in series with R Thevenin, which is 8 ohm. Okay. So therefore, I don't know if I can copy this. So basically what we did, oh no. So this circuit, no, anyway. So this big circuit that you see here, all this big circuit, from the point of view of A and B, can only be replaced by this Thevenin equivalent. Okay. Okay, so next is the Norton equivalent. Okay, so very similar to Thevenin equivalent. We need to calculate the R Thevenin exactly the same as how you calculated R Thevenin in the Thevenin method. Basically, they're the same techniques that you used before. But how about the I Norton? So for I Norton, assume again, on the left, you have your original resistive circuit, and on the right, you have the equivalent, the Norton equivalent. You have current source in parallel with the R Thevenin, okay? This is not A and B. Now, if I do the short circuit, let's say I externally short circuit A and B, now what would be the I of short circuit? We show it with ISC, I short circuit. So let's calculate I short circuit. So now everybody think about that. If I have this current source, I have this resistor, and then suddenly I short circuit this. Hopefully everybody agrees that because this R is short circuited, so I can just remove that. So basically there is no current here, I equal to 0, because it's shorted. And all the I Norton will go there. So I short circuit is equal to I Norton. If this is I Norton, if call it I Norton. So I short circuit is equal to I Norton. Okay, so therefore we can say that if I go back to original circuit and I do the same process, meaning that from node A and B, I short circuit it and then I'll analyze the whole circuit, and I look at the I short circuit, that should give me I Norton. Okay, that's it. So this is how therefore we can find Norton equivalent. We calculate the I short circuit, that's equal to I Norton. So for example, in this example, I short circuit it, I analyze the circuit, I find this current, and that's my I Norton. And then I have to find R Thevenin. How do I do R Thevenin? Exactly as before, you have to zero all independent sources. You get rid of the sources, independent ones. And then you look at R equivalent. Maybe you have to put a test voltage. Then you are gonna do that. You put the test voltage Vs, find Is, R equivalent would be Vs over Is. Okay, so previous example, the same example. Now let's look at the Norton equivalent. Okay, so just short it from A to B, you just connect them, and then you have to analyze the circuit. So again, any technique that you can think of here, you can use, but again, let's, for just as an option, let's do the node analysis again. So just reference node, and then this is another essential node, valid V2. Okay, so write a KCL here. So what's this current? V2 minus 25 divided by 5. That's this current, this term. And then going down, V2 minus 0 divided by 20. This current, negative 3. And also in this case, we have this current as well. So this current is V2 minus 0 divided by 4 equal to 0. Just one unknown, we calculate V2 as 16 volts. Okay, so this voltage from here to here, or this one is 16 volts. Okay, now what is the I short circuit? I short circuit is this current. If this is 16 volt and this is 0, so 16 minus 0 divided by 4 gives me this current, which is exactly this current, so which is 4 amp. Okay, perfect. So this way now we calculated this I short circuit, which is also equivalent to I Norton. So this is my current source. Now, how about the R Thevenin, as I said, is as before. We already did it with this example. We just zeroed the sources and we looked at the R equivalent. And the same process, you don't have to do it. If you already have it, you don't have to do it twice, right? Zero this, zero that, and zero that, open it, and then you look at the resistance, and it's as before, so it's 8 ohm. Okay, so now this is gonna be my Norton equivalent, node A and node B. We have current source with the amount of 4 amp in parallel with the R Thevenin, R equivalent, which is 8 ohm. Okay, so you see the difference between calculating the Thevenin and I Norton. For Thevenin, you have to do open circuit. You look at the open circuit, and then for Norton, you look at the I of short circuit. Okay, good. So now let's again look at all of them together. So this is the original resistive network that you had. This is the Thevenin equivalent that you just calculated. The whole thing can be modeled by an 8 ohm resistor in series with a 30 volt voltage source. And on the right, you have the Norton equivalent. The whole thing from point of view of A and B can be modeled with a 4 amp and then 8 ohm resistor in parallel. But also, because we already know about source transformation, we can see that actually we can apply source transformation going from one of them to the other. See the same R, and then V equal to RI. V Thevenin 32 equal to R 8 ohm times the I Norton. So this always can be applied based on the source transformation. V Thevenin equal to R Thevenin times I Norton. Okay. Okay, so this is another way of also looking at R Thevenin. Maybe then in some of the cases we can do that. If for some reason you have the V Thevenin, which is V open circuit, and you have I Norton, which is I short circuit, if you find a ratio, that gives you R Thevenin. Okay, so hypothetically, let's say somebody tells you, I know what my V Thevenin, I know my I Norton, then you can calculate the R Thevenin based on that. Okay, you have this relationship. Look at here. So V Thevenin is 32, I Norton was 4 amp, the ratio is 8. Okay, good. So this is for our first example. Now let's look at what we have next. Okay. Yeah, somehow again the summary that I mentioned. So V Thevenin is equivalent to the V open circuit, I Norton equivalent to the I of short circuit, and there is this relationship that R Thevenin equal to V open circuit divided by I short circuit. Okay, and this is a summary page. Again, so if you look at the open circuit, that gives you V Thevenin. If you look at the short circuit externally, you short it, calculate it, and then that gives you I Norton. And then the ratio of them can give you R Thevenin, or you can, so this is an indirect way. I call it indirect way, meaning that if somebody tells you this V opens V Thevenin and I Norton, you can find the ratio, indirectly find R Thevenin, or directly you can look at the resistive network and again, zero independent sources, and then look at the R equivalent by applying maybe test voltage Vs over Is, gives you the R Thevenin. So again, there are different ways of solving the same problem. And eventually, after you do this, you have V Thevenin series with R Thevenin, that's Thevenin equivalent, or we have current and then resistor in parallel, that's your Norton equivalent. Okay, perfect. So now let's look at example 2. So this circuit is given. Find Thevenin equivalent for this circuit containing dependent sources. Yeah, so we have dependent sources, independent sources, resistors, and you want to find Thevenin. Okay, good. From point of view of AM. So for calculating V Thevenin, you have to open it. Okay, so here it's open. And when it's open, it means that this current equal to 0. As you saw in previous examples, we use this fact that when it's open, this is current equal to 0. And okay, so we have to analyze the circuit to calculate this V of open circuit. So again, here, any method can work. Let's see what I did here. Okay, so V Thevenin is V open circuit, so call this plus and minus V open circuit, which is equal to V Thevenin. So from here to here, plus minus, which is exactly whatever voltage across this 25, right? The same as this V. This is the same as this, right? Okay, so therefore this voltage is equal to 25 times the current. So what is the current? I claim this current is this current, which is negative 25. So there's a current source here, right? This way. So negative 20I goes there because this is open, so that's 0. So all of it goes down. So therefore, my V of open circuit is 25 times negative 20I. 25 times the current, which is negative 20. 25 ohm, negative 20I. That's my V Thevenin, which is negative 500I. But it's a dependent source, right? So I, where is I? I here. So let's calculate I. Okay, it's a simple loop here. Let's write just the KVL. Negative, let's start from here, going up. Negative 5 plus 2K times I plus 3V equal to 0. Okay, so there's another dependent source. What was V? The V from top, that's the V. Remember, 25 times negative 20I, negative 500I. Okay, great. So you put this negative 500I, replace it here, and then there's just the one equation. There's unknown would be just I. After you replace it here, there's just I. You solve it, and gives you I equal to 10 milliamp. After you have the I, you replace it here and you get the Thevenin, which is -5. Okay. So as you see, we did step by step. So this voltage I repeated. This voltage open circuit was 25 times this current, -20I. Then I went to see what's going on with I. I saw there's a loop here. I wrote a KVL here. And somehow it depends on V. And then I used the V that I had here, there. And I calculated. Okay, again, there's not a unique solution. You might end up with doing something else, which is totally fine. Okay, very good. So we got the Thevenin. So now let's look at the I Norton. So let's look at the I Norton. So for I Norton, remember we have to do the short circuit. So just connect A and B here. So the same circuit, but just you connect A and B. And you calculate the I of short circuit. Okay, so let's examine the network a little bit. There is a short circuit here. Oh, okay, the short circuit is in parallel with the resistor. Hopefully everybody agrees that because this is short, then this current, this resistor is basically as if it's disconnected because there's no voltage across that. In other words, this V plus and minus V equal to 0 because it's short. And there's no current here, I equal to 0. It's like this, you can disconnect it, okay? I equal to 0. So therefore, what is this current? Again, like whatever this current was here, it was -20I, will end up to be here. So I short circuit at it is -20I, but of course we don't know what's I. I have to go back and check what's I. But that's the first step. Okay. So I short circuit is -20I, but here I was again going back to doing the same process, KVL, -5 plus 2K times I plus 3V equal to 0. But now the difference is that V now here, in this case, because it's shorted, V equal to 0. Good. So V equal to 0, so you get easily I, 2000 I equal to 5. I equal to 5 over 2000, which is 2.5 milliamp. That is this I, and then I Norton, I short circuit is -20 times that. -20 times 2.5 milliamp gives me -50 milliamp. Okay, very good. And this is my I Norton. Okay. So now, what is R Thevenin? R Thevenin is V Thevenin divided by I Norton. So basically, this is a just practice of finding R Thevenin by doing V Thevenin over I Norton. So, and alternatively, you would directly find R Thevenin by doing the test voltage, remember? I guess we might have its solution later on. Yeah, we did this also the other way, but this is just another practice. Practicing finding V open circuit as V Thevenin, then I Norton, I short circuit. And then given that we have both of them, with just the ratio of the V Thevenin over I short circuit, I Norton, gives me the R Thevenin, 100 ohm. Okay. So to wrap up, this is my Thevenin equivalent. This is the 100 ohm in series with V Thevenin. My V Thevenin was -5. Okay, so there are two ways of, so V Thevenin was -5, okay? So that's why, as you can see, I put the negative up, okay? So there are two ways of showing that. Either you can say the same notation that we have, negative and positive, and then they say, okay, V Thevenin is -5. Or you can just change the polarity and say, okay, this is plus and minus here, and it's 5 volts. So hopefully everybody agrees. Both of them are the same. This is the notation that we use, plus minus V Thevenin. Okay, so then you say my V Thevenin, whatever it is, happens to be -5. Okay, but just to make it not having a negative voltage, you can just reverse the order. You say, okay, I just change my reference, and I change this to plus and minus, and I make it 5 volts. Okay. Okay, so just think about it. Hopefully everybody sees that. So this one says this port is -5 volt, or this minus that. Just quick thing. Let's call it, I don't know, C and D. So this says VC minus VD, VC minus VD, based on this polarity, plus or minus VC minus VD is equal to this value, -5. Okay. So in other words, if you multiply both sides by negative, it means that VD minus VC equal to 5. Okay, so that's the other notation. Here, VD minus VC equal to 5. Okay, good. You can leave it either way. Either just leave it as it is, or just change the order so that you get rid of the negative. Okay. Okay, good. So that's our Norton, Thevenin equivalent. This is my Thevenin equivalent. Now, how about the Norton? Norton, we already had the I Norton, right? -50 milliamp in parallel with 100 here. So the same as before. You have this is the current source, and this is the parallel with the 100. And the current source happened to be, I Norton happened to be -5. Okay, so you can leave it as it is, or you can just change the order, like the direction of the current, to get rid of the minus here. If -50 milliamp is going this way, it means that 50 is going down. So that's why I changed the order here, and I just made it positive. Again, it's both of them are the same. However, you're more comfortable, you can leave it that way. Okay, very good. So this example was also a very good example, because we saw both calculating with Thevenin, the open circuit, and I Norton as I short circuit. Okay, good. So with the same exact problem, now let's calculate our Thevenin direct way. Instead of dividing open circuit over V open circuit over I short circuit, let's go to direct way as another practice, looking at our equivalent. Okay, remember what we said? You have to get rid of the sources, like independent one, the ones that generate like this. In this case, there's just one independent source. You get rid of this by zeroing it, meaning that you short circuit this. See, I shorted it. And again, remember, you keep the dependent sources, because dependent sources, they don't generate anything by themselves, right? So they are acting like a resistance. Okay. Okay, very good. So I shorted this and everything here. Now, because of the dependent sources, we have to put a test voltage, Vs, and I have to calculate Vs over Is. Okay. So you have seen, at this point, this is exactly as we have seen before to calculate the R equivalent. There's nothing new. Okay. Okay, so to solve this, again, any method can be used. Let's write a KVL on this loop here, So 2K times I plus 3. So originally it was 3V, but because I connected to the voltage source, V equal to V of S, okay? So 2KI plus 3VS equal to 0. That's one equation. But then, so you can look at another equation. So let's look at here. There's a note here. There's a essential note here. So we can write a KCL on this note. Okay, 20I, and then this voltage is V of S, right? Vs minus 0 divided by 25. and then minus IS equal to 0. Okay, so on this equation, there's an I here, but then I had I from the first equation in terms of V of S. So here you write I in terms of V of S, and then you replace it here, and that's perfect because now everything would be in terms of Vs and Is. 20 times negative 3 Vs over 2K, Vs over 25 equal to Is. So group all the VSs together and all other ISs together. So Vs times negative, you simplify this, I guess, negative 3 over 100 and 1 over 25 Vs equal to Is. Simplify, eventually Vs over Is is going to be 100. Okay, perfect. So that gives you the R Thevenin, 100. Oh, which let's check. Is it the same as these guys? Yeah, so see, from the previous technique, from this V open circuit divided by I short circuit, I got also 100. Again, this was an indirect way, but this is what we did here was direct way. I put the test voltage and I looked at Vs or Is. Okay, perfect. Okay, so now a note on when we put this test voltage. So I have mentioned here. Even you can put a test current source. Okay, sometimes it make it easier if we use instead of voltage source that Vs over Is, I can put a current source with a value of 1 amp. So previous years, we had some discussion problems on this that we would put that, I don't know, hopefully, I don't know, Lauren and Isaac have some, because they designed the new discussion problems, they have some examples on this. That, okay, so instead of putting a Vs, we put the Is and we put also, we give it a value to that, 1, let's say if it's 1 amp, okay, and then we calculate V of S. And the goal is that, okay, I find R equivalent. Now look at here. If this is V of S and this Is is 1 amp, so what would be the Vs? So all the 1 amp here goes here. So therefore, V of S, which is this, equal to R equivalent times the value of I of S. And I of S happened to be 1 amp. We just said, assume that this is 1 amp. So R times 1 is just 1 R equivalent. Okay. So in other words, if I put a current source of 1 amp, and if I measure the Vs, that's exactly equal to R equivalent. Just as another alternative. Again, hopefully you might have some question on this and discussion. But again, feel free to also do this technique, Vs over Is. Okay, perfect. Okay, so just to wrap up, to calculate R Thevenin, zero all the independent sources of energy, then you're left with just resistance. How can you calculate the resistance? You put a test voltage, either you put a test voltage and look at Vs over Is, or just today I told you, you can put a current source and assume Is is equal to 1 amp, then the Vs would be the R Thevenin. Third is if you happen to have V open circuit and I short circuit, just find the ratio of the options. Okay, very good. So now let's move on to the third example. So find the Norton equivalent. Oh, okay. This exam is Norton equivalent with respect to terminals A and B for this circuit. So this circuit is given. You want to find the Norton. For Norton, remember, we have to look at the I short circuit. So I just short A and B. From here to here, I short it. And I have to calculate the I short circuit. Okay. So because this is shorted and this is resistance, I hope everybody agrees that I can just get rid of this. And okay, so if we get rid of that, then you can just remove it. Then you get this circuit. You have the current source 8 and then 2, then it's shorted and then 10. So you have to calculate I short circuit. Just by looking at this, hopefully everybody sees a current division. There's a current source and there are two branches. If I look at this 2 and 10 as one resistor of 12 ohm, right? 8 and 12 are in parallel. So therefore, what is this current? This current is 8 divided by 8 plus 12 times 50. So it gives me 6 amp. So the I Norton would be 6 amp. So we did this. Now we have to find R Thevenin next step. So for R Thevenin, again going back to this original circuit, the first step is always to get rid of the independent one because we just want the resistors. We don't want any source of energy. Get rid of that. Current source, open it. You open it and then this is what is left. You have to find the R equivalent. So in this case, so if we get rid of this, open this. So what happens? These 2, 8, and 10, they're in series. And then, so it becomes 2 and 8, 10, and 10, 20. So 20 in parallel with 12. That will give us the R equivalent. So I have it here. So you opened it. Then when you open this, these three become in series, 2, 8, 10, 20. Then this 20 is parallel with 12. 20 times 12 divided by 20 plus 12 gives me 7.5. Oh, and that's my R Thevenin or R Norton, doesn't matter. And this is the Norton equivalent. You have the I Norton 6 amp, we got it here, and then in parallel with the resistor. So next example, this circuit is given. And we would like to find the Thevenin equivalent with respect to terminals A and B. Was it Thevenin or Norton? Actually, both of them. Find Thevenin and Norton equivalents. Okay, that's fine. So let's start with the Thevenin. Thevenin, remember we said we just do the open circuit. We have to calculate the V open circuit. Okay. So this is my circuit. This is call it V open circuit. Again, because it's open circuit, yeah, this is 0. So this is important. So we'll use it later probably. So we have to analyze and we have to calculate this. So this seems to be a good candidate maybe for a node analysis. Again, here is totally up to you how we are going to use it. But looking at this seems to be a good candidate, and I tell you why. How many, let's look at the essential nodes. So there's one essential node at the bottom. Okay, we equal to 0. There is one node here, voltage, we call it, let's say VA. And there is another essential node here, but look at here. This is connected to a 30 volt, directly connected to a voltage source, which is also connected to 0. So basically, I know this value. So that's the case that I remember I told you it's a lucky case. So this V is 30 volts. So therefore you don't have, in node analysis, when this situation happens and you know the value of this essential node, you don't have to write any KCL here anymore. It comes to you free. Okay, so therefore you don't have to write anything here. So the only node that you have to write the KCL for is this node. Okay, so therefore it seems to only have one equation. That's great. So let's write the KCL here. So I start from here. So VA minus 30 divided by 15 is this current. And then this current is 3 milliamp. This current is VA minus 0 divided by 5K. And then this current is 0. So I get this V open circuit comes to this picture here, that this current is 0. Okay. So all this equation equal to 0. Just one unknown, VA. You solve for VA. And I definitely recommend you doing this by hand yourself. Here, for example, the easy way is to just get rid of the denominator. So if I multiply this by 15K, the whole thing by 15K, then I will get rid of the denominator, right? So you get VA minus 30 and then multiply by 15K. So 15 times 3, 45. And then you have a K and a milli, they cancel. So it's just 45. And then 15K by 5 divided by 5K is giving 3. So 3 VA equal to 0. Okay, so from this step to that step, make sure you don't make any numerical mistake. Okay, and then you calculate based on that VA. So VA happens to be this. So we calculate this VA, but this is also equal to V open circuit, because open circuit, one side of that is anyway 0, and this is V of A. So V open circuit is just VA, and that's V Thevenin. So we found V Thevenin. That's great. And now next step is to find the R Thevenin. Okay, so let's do R Thevenin direct way, meaning that you get rid of all the independent sources. You zero them. Zeroing a current source, you just open it, open. Zeroing a voltage source, you short it. Okay, so if you do that, your circuit extremely simplified. You get rid of this, and then you short this, you get rid of that. So basically you have the 5, you got rid of that, you have the 15, and then you short circuit at this, and then you had still the 10K, and then you open this. But then the 10K was just shorted, so that's why I didn't even plot it. Okay. So now this is your circuit. You have to find the R equivalent from this point of view, A and B. If you look at here, these two are in parallel, right? One side and the other side. 15 and 5 are parallel. You multiply by 15 times 5 divided by 15 plus 5 gives you 3.75 kilo ohm. Okay, so this is one way of finding R equivalent. So therefore, now your Thevenin equivalent, this is your V Thevenin. V Thevenin happen to be negative, so you can just leave it as this way, plus and minus, and this is your V Thevenin. And R Thevenin happen to be 3.75. We calculated that. So this is your Thevenin equivalent. Now at this point, if somebody tells you, okay, how about the Norton? Okay, so because you already have V Thevenin and R Thevenin, you can just go with the source transformation idea, basically V equal to Ri, or I is equal to V over R. V Thevenin divided by R gives you negative 1 milliamp. So therefore your Norton equivalent is negative 1 milliamp in this direction. Again, you can fix the direction vice versa, but you don't have to. And then in parallel with the R equivalent. Okay, very good. So for the big circuit that you had from in the top, this you can model it from the point of view of A and B. Looking here, you can model it with this circuit or with that circuit. Thevenin equivalent or Norton equivalents. Okay, okay, so now we want to practice finding I Norton direct way. Okay, so let's do that as a practice. So we are just doing, as you see, this class is about practice, practice, practice. Okay, so now let's find I Norton direct way. So for I Norton, remember, we have to short circuit. So I connect A and B together, and I have to calculate I short circuit. So again, just looking at the circuit, similar to before, volt voltage analysis seems to be a good option because all of this, you can reference it as 0. And then because of this 30 volt here, this is the lucky case, remember? So this gives me 30 volts. This essential is all 30 volts. And interestingly, what is the value of this? It's short circuit, right? It's short circuit. So all this voltage is also 0. Okay. So this is also 0. But then anyway, because I want to calculate I short circuit, so let's write the KCL here. Okay, so let's write the KCL on this node. So here gives me 0. This is 0, right? It's short circuit. 0 minus 30 divided by 50. 0 minus 30 divided by 15, that current. Then current going down 3 milliamp. This current, what is this current? This current is 0 because it's shorted, right? Also, you can say this is 0, this is the 0 minus 0 is 0. So the current here is 0 because the voltage is 0. And now this current is I short circuit. Okay, I short circuit. The reason that I wrote this equation to find I short circuit. So from this equation, I short circuit is happen to be negative 1 milliamp. Okay, this is the direct way of finding I short circuit. And now again, going back and checking the R Thevenin is V open circuit divided by I short circuit. V Thevenin I Norton, you get the 3.75K. Okay, as we calculated the other way. Yeah. Okay, perfect. So these were all the notes that we have on finding the Thevenin and Norton equivalent. So you got the idea and what's the concept. Again, I just wrap it up. For Thevenin, you have to look at the V open circuit. For Norton, you have to look at I short circuit. And then we saw a lot of examples on how we can handle this. Again, all the techniques that you have learned so far can be used here to basically analyze these circuits. Okay, great.